we want to go a bit bigger. So we want to generate a larger 2D deterministically generated discrete variable cluster state. So how are we going to do it? Well, we're going to start with two physical transmon qubits coupled to one another and tunably coupled to a waveguide. The waveguide will allow us to emit the state of these two transmon qubits as flying photonic qubits. So this architecture is going to permit us to generate a ladder-like structure of entanglement, you can see on the graph there, and we'll be able to generate a 2 by n size swap between a source qubit and an emitter qubit. Now I label the states of the source qubit as G and E, and the states of the emitter qubit as 0 and 1. And to enact a swap operation, what we do is we modulate the coupler C1 at the difference frequency between the E0 level and the G1 level. And what this allows us to do is actuate a parametric sideband transition between these two levels. And if you remember, the emitted qubit has a very, very short coherence time. It will decay on the order of about 100 nanoseconds, and we'll go back to the G0 state. So what this means is effectively we've swapped the state of the source qubit into the waveguide that's now emitted its state as a flying photon. And if we look at that in quadrature detection, we'll see something like this. So this is the signal in the I quadrature after down conversion from around about 5 gigahertz to an intermediate frequency of 300 megahertz. And that's the oscillation you see there. So we can also do the same thing, but create a C0 gate by driving the F0 E1 transition. So now we go to the second excited state of the source qubit. And what we do to enact a C0 is we pass from E0 to F0. We do the same parametric sideband transition idea, but this time between F0 and E1. And of course, the moment we get to the 1 state on the emitted qubit, we fall back down to E0 and emit a photon. Now, the key difference here with this gate to the previous gate is the fact that if we were to start in the G0 state, we wouldn't have emitted a photon, but of course, if we start in the E0 state, we emit a photon, so it's a conditioned emission, and it's conditioned on the state of the source qubit. So we've got a C0 gate between the source qubit and an emitted photon. And again, if we look at that in quadrature, it actually looks much the same. You see this photon envelope, this rise and fall as the photon gets emitted and decays into the waveguide, and this modulation, which is the intermediate frequency of the field that we measure. And finally, the last gate we do is the source gate. And what we do is another parametric sideband transition, this time between EE and FG. And this one will be perhaps a bit more familiar to people. We do a 2-pi rotation on that transition, and this gives us a conditional phase on the EE state. So how do we generate our 2D cluster state with these gates? Well, we start with the 2 source qubits, and we put them in a superposition state using a Hadamard on each one of them. Then we do our C-phase gate to entangle the 2 qubits. We apply a C0 gate, and every time we apply a C0 gate, we generate a new pair of photons. So we've added P1 and P2 on this diagram here. And we can repeat this process over and over again. So we add another pair of Hadamards, another C-phase entangling gate, and another pair of C-knots, and we add another pair of photons. We can just keep doing this over and over again and adding more and more entangled photons to our state. And when we're done, we can finally swap the state of the two source qubits into the waveguide and disentangle the entire chip from the waveguide, leaving us with an entangled flying photonic state. So what does that look like when we actually detect the fields? Well, remember we've got two emitter qubits at different frequencies, and I only showed you one at a time just now. And we've only got a single emission line. So what we're doing is actually we're going to frequency multiplex this emission line so that we can detect photons from both emitter qubits simultaneously. So if we emit 4 entangled photons, if we were to do the measurement, well, this one wasn't an entangled state, but if we emit 4 photons, it would look something like this. So you can see 2 photon envelopes in time, but within each one of these, there are 2 distinct frequencies. So if we take the Fourier transform of that, we see 2 clear peaks. Each peak corresponds to the frequency of the emitter qubits. So how do we go from this then to determining what the actual state was that we generated? Well, as I've shown, we measure the I and Q components of each photon. Here I only show the I component, but we also measure Q. And for each one of these, we know the frequencies and the times at which we expect the photons, and so we perform a weighted integration. And so in this particular case, we've got 4 photons. We would extract on every shot 4 pairs of I and Q values. Now, we do this over and over again to get lots of statistics, and we compute the moments of the field operator and truncate up to a maximum of 1 photon per mode. And we perform convex optimization on these moments to turn these into the most likely physical density matrix. So what's the actual result? Well, here I'm showing you a 4-photon cluster state, so this entangled in 2D. And above the diagonal, above this zigzag line, we've got the ideal state. And below the diagonal, I'm showing the actual experimentally generated state. And so for this particular state, we got a fidelity of 0.86. And you can see there that the pattern is very, very clearly matching what we would expect for the ideal state. And the imaginary component is very close to 0 for all values. So I'm getting towards the end of the time for the first part of the talk. But in conclusion, what I've shown you is that we've built a machine that can entangle microwave photonic qubits using only 2 source transmons. And this gives us a 2 by n size entangled microwave photonic state. It's based entirely on superconducting circuits. We've got a deterministic emission protocol. We detect our field in quadrature, and we can do direct tomography using the calculated moments on up to 4 photons. Now, you might be asking, what about more than 4 photons? So kind of the point of this device is that we can go a bit further than this. And you're going to have to stay tuned for the next talk to find out how many more we can actually get and how we figure out how many we've got. Yeah. So thanks for your time.
Okay, if people have questions for the first part, please come up to the mic.
So it's a good talk. Thank you. I'm looking forward to the second half. Hopefully it'll come sooner than Dune 2. You talked about a specific graph structure here. How tightly related to that is your actual hardware topology? Can you do other graph states with this?
Yes, so in principle, yes, we can. I mean, what I've shown here, obviously the device is specifically designed to generate this kind of ladder-like state, but depending on the gates that we actually choose and the order in which we apply things, it is possible to generate other states. For example, we think that we can generate repeater states and tree graph states, and it might even be possible to generate 3-dimensional entanglement, but because the device is not optimized for that, it probably wouldn't work as well as this cluster state, which is what we really built it for. But in general, yes. So we can generate quite a lot of other states in principle.
Thanks.
Yep.
Hey, thanks for the talk. Your fidelity is pretty good. Is there one gate that particularly limits it, or are they all kind of the same?
They're actually all pretty limiting, if I'm honest, even the single qubit gates. So there is a reason why. So our two source transmons are very, very close in frequency, which is good for us in some ways, but also actually limits us for other reasons. But yeah, essentially, the more photon emissions we perform, the worse it gets, and they all uniformly need to be improved. I think it's predominantly gate errors rather than coherence time errors that we're suffering from that affects our fidelity. Yeah.
Thanks.
Yeah.
It seems like in your architecture it relies a lot on having one qubit that has a fast decay time Yes, so the decay rate is simply just the amount of coupling that we apply to the waveguide. It's fixed, we don't control it. We simply design it to be approximately on the order of 100 nanoseconds sort of decay time. If we wanted it to go faster, we could increase that coupling. In practice, then we would just become limited by our gate time. So there's not much benefit to go significantly faster than the gate time because we don't gain much. So that sort of motivates why we chose that coupling.
Where you show the photon amplitudes, you show one photon after the other, right?
Yes.
Do you have a good understanding of why they have different amplitudes?
Yes, so if you look at the two, here we are, yep, these two photons. This particular state was emitted with an F0E1 transition here and the E0G1 transition right here. And actually the F0G1 is a little bit faster just because it's using the F state. And that means that the photon amplitude increases faster and reaches a slightly higher maximum. And that's why you get a slightly different shape. But it's really just the emission, the emission gate that we use that dictates that.
How do you calibrate the absolute gain of the output chain?
Yes, very good question. So we have two methods. We can use, for example, a Fock state. So we could emit a Fock state and say, we think that this is exactly one photon. We measure the moments of that and scale everything according to that single Fock state. But this is kind of assuming that our emission is working very, very well. So what we can also do is continuous wave drive the emitter qubits and get basically a mono-triplet spectrum in this sort of photon blockade regime. This allows us to calibrate the scale of the emission. Yeah. And we find that they match quite well. I haven't shown it here, but they do match quite well.
Okay, so for the second part of the talk, I'm going to welcome James again.
Yes, thanks. So, my name's not Alexander Grigorev. Unfortunately, he was unable to make it due to visa issues, which is very sad. So I'll have to give his part of the talk for him. You just have to pretend that I'm speaking with a Russian accent. So Alexander is a PhD student, also in the QDev group at ETH Zurich. This part of the talk will focus on the characterization of these deterministically generated two-dimensional cluster states. So just to quickly recap, we're interested in large-scale entangled states for the purposes of measurement-based quantum computing, but also other things like robust quantum communication, quantum metrology, etc. We've shown that we're able to generate a 2D cluster state using a pair of source qubit transmon qubits tunably coupled to a waveguide. And we directly detect the fields in quadrature and compute the moments of the field and use this to reconstruct density matrices of entangled states. So what I showed you in the first talk was a reasonably high fidelity 4-photon entangled state. And what we want to know is, how can we go beyond 4 photons? Now, it gets a bit problematic going beyond 4 photons because it's actually very, very difficult to measure all of these multi-qubit correlators. And what we find is that it's actually, yes, it's very impractical. And what we want to do ideally is to restrict ourselves to only measuring 4-photon subsets of the whole state, but see if we can still reconstruct the whole state and figure out what's going on. So if we take a 6-photon state, for example, like this, what can we do? Well, we can take advantage of the fact that the cluster state is the ground state of this Hamiltonian here. And there are only nearest neighbor interactions present. So this doesn't work for every state, but for this particular state, and a variety of others actually, we can do 4-photon tomography, so we can reconstruct the state of subsets of the 6-photon state. For example, this subset. And this is the experimental result here. So again, I'm using the same convention I used in the first talk, is that below the diagonal, we've got the experimental state, and above the diagonal, we've got the ideal state. So this 4-photon subset looks like this, and we can do this for all nearest neighbor 4-photon subsets, so these T-shaped ones in the middle, and the other square on the other side. So these are all the results that we get for this particular state. And what we can do is then use another round of maximum likelihood estimation to go from these 4-photon subsets to the global state. So this is what we get for a 6-photon entangled state using this method. So we've managed to reconstruct a state that's larger than the actual individual scale of the moments that we're using. Now, this pattern is kind of a bit complicated, so maybe we'll just take a step back quickly. And what we did to sort of get a better understanding of what's going on is we ran multiple 6-photon state generations, but we turned on different gates to see what's going on. So we can start from a completely unentangled 6-photon state where all the qubits are in a superposition. So the gate sequence is going to look like this. And we get a reconstructed state that's basically just a big square of red. Now we can turn on our first entangling gate, so this is this CZ gate over here on the left, and we start to get some more structure in our state. We can turn on another few gates, and what we've got here is a 4-photon entangled state and 2 extra photons that are not entangled at all, and it's no coincidence that it looks very, very similar to the state that we saw before. And finally, we can turn on the last 3 gates, and we arrive at that 6-photon state, and we see how the pattern has finally emerged from there. And for this state, we get an 82% fidelity. So if we want to go even bigger, we run into more problems. So the density matrix is starting to become very, very big, and it becomes quite impractical to process. In actual fact, if you get as far as 14 or 16 photons, it's pretty difficult to even fit it on your PC, let alone do anything with it. So we have to be a bit cleverer, but fortunately there are clever people out there who've already thought about this. So we use the matrix product state formalism to deal with larger states than this. So this is a formalism that allows us to efficiently describe the relevant part of the Hilbert space that our cluster state lives in. And we can also extend this to the notion of mixed states if we use matrix product operator formalism, basically. In practice, actually, what it means is that besides using this matrix product state formalism and dealing with the density the states in a slightly different way, we still use the same procedure. We calculate the 4-photon moments of all the subsets, and we reconstruct the state, but we do it inside this matrix product operator formalism. And this allows us to go larger. So, for example, we've got an 8-photon state here. Now, for the same reasons that the density matrix is difficult to deal with, it's also difficult to visualize. So I'm only going to be showing the first 6 photons of the states from now on. And that effectively means that we're showing the top left corner of the density matrix as shown in this schematic here. Again, remember, below diagonal is the experimental, and above diagonal is the ideal state. And one other subtlety of this plot is that I've now switched to showing the phase of the state, not the real and imaginary components. The reason for this is due to decay on these much larger states, it becomes very difficult to actually see the pattern unless we plot the phase. But if we plot the phase, we can see the pattern emerging quite clearly. So this is this 6-photon subset of an 8-photon state. We can also go to 10 photons, and we see the fidelity at the top here dropping as we go to more and more. 12, 14, 16 photons, and we still see the pattern still appearing. But the fidelity has really, really dropped. And you may already be aware that if our fidelity is below 50%, we can't actually claim genuine multipartite entanglement. So how do we know that this is actually an entangled state? We need some metric of how entangled everything is. So we use a metric of localizable entanglement. So first of all, we reconstruct these states in the MPO representation, and then we're going to use this state and try to extract some metric that allows us to estimate the maximum length of our state that still preserves some meaningful measure of entanglement. So how do we do this? Well, we choose the diagonally opposite qubits of our state. So on here we see the top left and the bottom right qubits marked out by these red circles. These are the two that we're going to choose and measure basically the bipartite negativity between these two states. So we have to, in order to do this, we have to project out the intermediate qubits, all the ones in between that we're not interested in. We project them out, and the basis along which we project them out. Well, I won't go into this too much, but it does matter which basis you choose, and actually we choose all the possible relevant bases and take the mean of all of those. But I won't go into that too much because it's a little bit beyond the scope of this talk. But after projecting these out, we end up with just these two diagonally opposite qubits, and we calculate the negativity between these two. And we can plot this as a function of the number of photonic qubits. So the ideal state, we would expect this value of localizable entanglement to be about 0.5, well, not about, exactly 0.5. And for our experimentally generated states, we see that as we generate a larger and larger state, this value falls off and eventually hits 0 around 16 or 18 photons. Now, we can try to verify this and see what we would expect based on process tomography. So we did process tomography on those gates that we repeat over and over again to generate the large state. And assuming that those gates stay the same and we just repeat the same operation over and over again, we can predict how much localizable entanglement we would expect for an n photon state, and that's shown in green here. Oh, and one thing I didn't mention also is that the circles are the different bases along which we are projecting the intermediate qubits, and the square is the mean of all of those different bases. We see these process maps are predicting this level of localizable entanglement. We also added a master equation simulation, and here you can see the coherence limit. So this is what we would expect if we didn't have any gate errors and everything was just limited by T1 and T2. So you may notice that the process map and simulation don't really agree very well with the experimentally generated localizable entanglement. There's quite a strong deviation beyond about 6 or 8 photons. At the moment, we actually don't fully understand exactly why this is, so we think that it's due to slow drifts in our experimental parameters over the course of the experiment. These experiments take a long time. We have to do a lot of shots to generate enough statistics on a 16 or 18 photon state. And over that time, we think it's possible we've seen evidence that there are some phase drifts and room temperature electronics are also affected on this kind of time scale, but we're not entirely sure exactly. So this is still an ongoing investigation. But the main takeaway point from this is that we can verify that we've got 12 photons entangled and verified with this localizable entanglement metric, and possibly even 14 photons, although 12 is definitely non-zero beyond error. So we were quite happy with this number of photons. So in conclusion, what I've shown you is that we've built this source of two-dimensionally entangled photonic qubits. We perform efficient many-photon tomography using the matrix product state formalism. We measure non-vanishing localizable entanglement for states up to 12 photonic qubits. And for an outlook, what we want to do is we want to further improve our generation and detection performance. Ideally, we want to also identify the cause of this discrepancy and see if we can get these purple points to match up with the process map and the simulation. We want to look into generation of other types of graph states, which we believe are possible, as we mentioned in the previous round of questions. And perhaps even take 2 of these devices and plug them into one another and have one of them emit a state and the other one absorb it and communicate these kinds of states between 2 distant devices. So thank you for your time, and I'll take questions.
If you have questions for any of the 2 parts, please come to the mic so that everyone can hear your question. Or shout out loud if you can.
The lifetime of this cluster state is how big and how it scales with the size of the cluster state?
Yes, so because what we're doing is we're actually sending the state directly into the detector. Now, we're allowed to do this by the deferred measurement principle, basically, that effectively what we measure is the same no matter when we perform these measurements. The actual entire state never exists at the same point in time. The photons basically immediately hit the detector while the rest of the protocol is still running. So we haven't actually got a measure of how long the cluster state lives because it's going straight into the detector. We would need to put it into some sort of delay line or a memory to have an idea of how it's behaving if we wanted to do that. But in this experiment, we don't have that sort of measurement.